We'll join from here as well. As I'm looking for the downstairs. Personal room, right? Yes. Sure. Good. The meeting, this is that. The ID. Is it? Well, that was just.
Need this one.
Well, you do. Yeah. Okay. Hi.
Hello. Today's speaker, I'm Latham. Nice to meet you.
Hi, Victorian.
Okay.
Retired professor here who worked in cosmic rays.
Oh, cool.
So I might get something out of this talk.
Yeah.
I will join the meeting.
Hopefully,
I'll go in a
hopefully.
different room and I pretend to be speaking languages.
Okay.
Okay, so we can
go over there.
Yes.
Why not from here?
Because it's both.
He wants to.
Yeah, we'll get that feedback.
And you're gonna come back then?
Yes.
Okay. Oh, we probably don't want.
Can you hear me?
Yes.
Can you hear us?
Okay, I can hear you loud and clear. So I suppose whoever is joining the meeting won't have any problems. Okay.
Good. I think so. We can hear you clearly.
Is that okay?
Yep. Thank you.
You are coming through very well.
Something fun.
Okay.
Should I stop and start recording?
As you
How
wish.
are you? Long time no see.
Yeah. Well, I thought you were.
Getting us in public, so I thought you'd pop by.
Are you? Where are you now?
I'm with Britta.
Okay. Right. That's right. How's that going?
Yeah, getting settled in now.
Uh-huh.
Starting to actually look at doing some work.
So it's a great pleasure to have Latham Boyle as our speaker today, visiting us from University of Edinburgh. Latham has worked on a variety of interesting topics, including the quasi-periodicity of Penrose tilings, structures in the standard model originating from theories such as non-commutative geometry, and restoring CPT symmetry to our universe, which is related to what he's going to talk about today, which is how the Big Bang is a kind of mirror. Please go ahead.
All right. Well, thank you so much, Yasaman. Thanks for the invitation to be here. This is my first time at DIAS, and I've already fallen in love with the building and the place. So I want to explain. Zoom is telling me I'm muted. That's fine, right?
Yes.
Okay. So I wanted to explain an idea that I've been working on with my primary collaborator on this topic, Neil Turok. A proposed picture of the early universe that we've gotten more and more excited about over the past several years as we've gotten to understand it more. And let's see, the subtitle, so the title is "The Big Bang is a Mirror." The picture in brief is that the Big Bang, if you think about it as a surface that's kind of mirror in time, or really a CPT mirror, that turns out to explain a number of the observed features of the early universe. So this is a proposed alternative to the inflationary theory of the early universe, which is the most popular picture of what went on at early times. And yeah, the subtitle is what is the simplicity of the early universe trying to tell us? The early universe is observed now to be extremely simple in basically every way that we've thought or been able to check. And that's the question is, what is that hint trying to tell us? And this is a proposed answer to that question. So I'll try to explain why we think that. Okay, so for starters, I just wanted to give this is a cartoon picture of the expanding universe. So the cone here is time runs up the page. Actually, it's really the formal time coordinate tau that cosmologists like to use that's running up the page. And the cone is supposed to show the universe expanding and as time goes forward. And so we're standing here at the top of the diagram. So that's us today, long after the Big Bang. And we look back with our telescopes toward the Big Bang, which would be the putative tip of this cone. And because the universe, we can't see all the way back, but we can see very close, depending on how directly depending on exactly what you mean by see, we can see more or less close to the tip. But one way or another, we have very good evidence that if you follow this cone back to a fraction of a second after the Big Bang, and you look at a time slice at that moment, indicated by this little tiny picture of the cosmic microwave background map from the Planck satellite, a fraction of a second after the Big Bang, that three-dimensional snapshot of the universe was ultra simple, and I've just summarized some of the crucial ways in which it was very simple. So first of all, to a first approximation, there were tiny bumps and wiggles in the temperature as you go from place to place, but if you ignore those first and just talk about what the background geometry and physical conditions look like, they were maximally symmetric. So that 3 geometry was maximally symmetric. So cosmologists say it was homogeneous and isotropic, basically the same if you translate from position to position. So the temperature was the same everywhere, the density was the same everywhere, the curvature of space-time was the same everywhere, and isotropic, meaning that it was the same in every direction every three-dimensional direction you would turn and look. And moreover, it was spatially flat. So it's basically the geometry was essentially a copy of three-dimensional flat Euclidean space. And then if you look more carefully, there's tiny little perturbations from place to place in the universe, tiny little, the density isn't quite the same everywhere. It's slightly more dense or less dense as you move from place to place. But so first of all, those fluctuations were tiny. They were about order 10 to the minus 5. They appear to be completely random, drawn from just a random draw from a probability distribution. And that probability distribution is also as simple as can be in all the ways that we've thought to check. So first of all, it seems to share the maximal symmetry of the background. So the probability distribution is also homogeneous and isotropic. The perturbations could have come in a variety of different types. There's density perturbations, or what cosmologists call scalar perturbations, basically changes in the temperature or energy density from point to point. That's the only perturbation that we actually do observe to be non-zero. There's other types of perturbations that could have been present, so-called vorticity or vector perturbations, meaning vorticity in the fluid flow at early times. We don't see any evidence for that. Also primordial gravitational waves, or what cosmologists call primordial tensor perturbations. We don't see any evidence for those so far. So they're purely of scalar type. And then the probability distribution they're drawn from appears, as far as we can tell, was perfectly Gaussian. So because it's a Gaussian probability distribution, the only thing that needs to be specified then about it is the 2-point function, the 2-point correlation function. Everything else follows from that. And the 2-point correlation function was also appears to be as simple as can be. Namely, It seems to be a pure power law as far as we can tell so far. No evidence for deviation from a power law. And moreover, it was what cosmologists would describe as a scale invariant power law, meaning that the power law goes like the distance to some power, and that power is such that the contribution to the perturbations from each e-fold that you expand, that you increase in scale is the same, independent of e-fold. It's almost scale invariant. It actually is observed to differ from scale invariance by a few percent. That's one of the only observed deviations from the really absolute simplest initial conditions we could think of. And then finally, this is an important point, this last point, that the phases of the perturbations, the temporal phases of the perturbations, are synchronized. We're synchronized in the far past in a very important way, which is that, so if you imagine taking the primordial density field and decomposing it into its Fourier modes and focusing on one Fourier mode, then the amplitude of that density perturbation, as you follow it forward in time, it oscillates. And now as you follow that oscillation back in time, its phase is observed to be the case that for every Fourier mode, if you follow it back in time, its temporal phase is such that as you follow it back to the beginning of the radiation era, i.e. to the Big Bang, it was at its maximum with zero derivatives. So in other words, it obeyed a Neumann boundary condition, or basically what we would ordinarily call a reflecting boundary condition. So that's why I say here it's synchronized exactly as if the Big Bang was a kind of mirror. Okay, so that's the basic clue that observations give us, that in short, the earlier you look, the further back you look, it seems like the universe is getting simpler and simpler as you get closer and closer to the Big Bang, in the ways described here. And that's the basic clue in early universe cosmology. So that's the fundamental clue, and the question is, what is that clue trying to tell us? So, according to the conventional picture, most models of the early universe, the picture taken by most models of the early universe, including the sort of most popular inflationary picture of the early universe, the clue is interpreted as follows. In those pictures, you say, well, okay, as far back as we can see, things were getting simpler and simpler, but that's kind of an optical illusion due to the fact that we can only see so far back. If we could see further back, according to that story, we would see that, okay, things were seeming to get simpler and simpler, but then they got messy again in the far past. And that the initial state of the universe was a big mess, and that the goal of a model of the early universe is to sort of put some cosmological physics here in between the big mess that at early times and the very simple state we actually see, to explain how the big mess got cleaned up and turned into the simple thing we see. And so the most famous example of that, the most popular example of a model like that is the inflationary model, which, as I've drawn here, the idea is there's a hypothetical proposal is that there's a hypothetical period of inflation in which the early universe undergoes accelerated expansion, basically stretches very fast. And the idea, roughly speaking, is you stretch out the mess so much that if you look at our past light cone today, it ends up only intersecting such a tiny bit of the mess that you sort of can't see what a big mess it actually is. Okay, so you're sort of restricted to look at some very tiny bit of the early mess within your past light cone, and you can't see that on larger scales it actually is a big mess. So it's important to emphasize, though, that there's absolutely no theoretical or observational evidence for this early mess. I mean, there's just no good theoretical reason to expect it's there, and there's absolutely no observation that there was anything messy in our far past. All the observations just are compatible with this ultra simple picture I mentioned. So, it's important to remember that this initial mess could be just a figment of our imagination, and designing a cosmological model to sort of clean up that mess could be a red herring. And so we've gotten interested in trying to follow an alternative picture, which is to sort of take the observations more at face value. So all observations so far seem to suggest that the further back you look toward the Big Bang, that the simpler things got. And so maybe that's just what the universe is trying to tell us. Maybe it's trying to tell us that that is what was happening, that as you follow things back to the Big Bang, that they just got simpler and simpler, and for some reason the universe emerged from a particularly simple initial state. So let's start by suppose we take that perspective and try to think about what that initial simple state was like and what exactly it might be telling us. Well, again, to interpret it, I want to start with this last clue that the primordial perturbations were synchronized in the way I described before. So that clue is represented in this famous picture here, which is a picture taken by the Planck satellite, a cosmic microwave background experiment of the so-called power spectrum of the temperature perturbations in the cosmic microwave background. And so we don't need to get into the details of exactly what's being plotted here, but suffice it to say that there's a theoretical curve that you see oscillating, and then the data beautifully agrees with that curve. And so why is that curve oscillating in the way it does, and why are there peaks at certain angular scales and troughs at other angular scales? And the answer is because of this. It's exactly because of this synchronization at early times. If you to explain this curve, to predict this curve, you're exactly assuming that at the beginning of the radiation era, everybody was synchronized in this way, and then as they went forward in time, because certain modes oscillate faster than others, different modes were at different phases of their oscillation at the moment that the universe took a snapshot of itself with the so-called cosmic microwave background, and that's why certain angular scales appear to be at maxima of their density fluctuations, and other angular scales turned out to be at minima when that snapshot was taken. But as mentioned before, the phases responsible for that are essentially reflecting boundary conditions. So another way to interpret that is just to say, in inflation, in this inflationary picture of the early universe, one explains those initial conditions again by saying there was an earlier epoch of accelerated expansion. The modes got stretched outside the horizon during that expansion. Perturbations got stretched to very long wavelengths relative to the so-called Hubble radius, and as a consequence got frozen to nearly constant values, and that's why at the beginning of the radiation era they had zero initial time derivative. But we just want to consider this alternative perspective, which is just a more simple and direct interpretation of the same observation, which is that if they satisfy an initial boundary condition, which is a reflecting boundary condition at the Big Bang, that seems, another way to interpret that is it's just telling you that the Big Bang is a kind of mirror. So we want to take that perspective and see where it leads. So it's important to say that this mirror, because it's zero derivative in the time direction. This is a mirror that, unlike an ordinary mirror where the normal direction is a spatial direction. So that this is a mirror where the normal direction is a time direction. And so yeah, so it's a mirror that reflects you in time. But other than that, the usual mathematics of mirrors apply. Yes.
I see what you say, that more of a derivative condition. It's just a little bit stretching things to call that a mirror.
Well, let's.
It suits.
I'll explain more. What? Yeah. Mm-hmm.
It suits your framework where you have like a mirror. You don't have to jump from the gun side.
Yeah.
Well, language, I know.
Well, it depends. Yeah, I guess it depends. It depends what you mean. But I'll maybe explain. I'll explain the sense in which if you assume that it seems to explain things about the early universe, and then you can tell me whether you would call that a mirror or not.
Yeah, but at the moment it is just one point about this group.
That all the, exactly. At the moment, it's that at the moment the only thing I've said is that all the fields, all the cosmological perturbations seem to satisfy. It's just, at the moment so far the only thing I've told you is that the density perturbations seem to obey a reflecting boundary condition. Yeah. But just to say, I mean, it is, you know, when you, I mean, maybe to, I mean, to the fact that you see, you know, an image of yourself in an ordinary mirror, I don't need to tell you anything more about the mirror than that the electromagnetic fields satisfy reflecting boundary conditions of the mirror. It follows from that. So I'm not sure there really, how much more there really is to it, but there's an additional question of whether it's an actual surface of reflection symmetry, whether there's an actual copy of anything on the other side of the mirror. That's a much.
And what is being reflected, and is there anything being transmitted? I mean, all those things.
Exactly. Good, very good question. So let's get to that. Let's get to that. One thing. A few more things before we get to this. So, okay, so the next thing I wanted to say was that if you take this picture seriously, that we're just going to follow the radiation dominated phase all the way back to the Big Bang, not put any earlier inflationary phase before it, then we know what the metric looked like at early times near the Big Bang, and it basically looked like this. So the metric was just proportional to the flat Minkowski metric times an overall conformal factor, and the tip of the cone corresponds to the fact that if you follow that conformal factor, scale factor A of tau back to time tau equals 0, that A vanishes, but also it vanishes, so it momentarily vanishes at tau equals 0, but it does so in the simplest way. It's just proportional to the conformal time. So it just has a sort of simple but analytic pole as a function of the conformal time tau. So for example, if, as we will do later, you just imagine tau, you consider tau as a function of, you analytically extend to the complex tau plane, and this is a simple 0 at that point, and there's no ambiguity about how to analytically extend through it. So unlike most singularities in GR, where you really can't, there's no well-defined analytic extension across the singularity, here this one is so simple and special that it's really unambiguous how to do it. So if you just let tau extend, again, out into the complex plane, and in particular to negative values of real tau, then you get this kind of double cone picture. And the thing which you notice about the double cone, if you take this analytic extension seriously, is that it has a new isometry that you didn't notice before when you were just looking at the top of the cone, which is the isometry tau goes to minus tau, which basically flips over the hourglass. Let's try to take it seriously, continue to think about the possibility that, and see where it leads us, see what it does or does not explain. So as a first step, it's helpful to use Roger Penrose's trick here, where we switch to a so-called Penrose diagram. So that's this trick where you can conformally rescale the metric in a way that stretches lengths, but in a space-time dependent way, but keeps locally angles preserved. So the Penrose diagram for this space-time looks as follows. Basically, we've taken the cone and stretched it out so that what used to be the point of the cone has been stretched out into this dotted circle. So that's the Big Bang surface now. So again, we want to take the perspective that there is an isometry that now relates. Okay, well, in the previous cone picture, it would have related a point up here to a point down here, but after this conformal rescaling, it relates 2 points like so, across the bang from one another in time. And then you find out, well, first of all, as we already mentioned, if you demand reflection symmetry of all the cosmological perturbations across this surface, you find that for the actual perturbation we observe, it gives the right initial condition to give the ringing spectrum observed in the CMB. But in addition, is there a question? Did I hear anything? But in addition, it turns out that same boundary condition implies that there's no primordial vorticity perturbations. They're incompatible with that boundary condition, which is good because we don't observe primordial vorticity perturbations. And there's no singular perturbations. In principle, there could have been singular perturbations both in the density and in the gravitational waves, which would have made the early universe look very inhomogeneous or anisotropic. And those are also killed by the reflecting boundary condition, which is good because we don't observe either of those phenomena either. So yeah, I just want to emphasize that the reflecting boundary condition also explains a number of the other observed properties of the primordial perturbations that we don't see.
So I'm not an expert in this, so I don't want to interrupt you much, but does it really explain those things, or it just makes it unnecessary to assume? That's what I worry about.
So what I mean to say is that the reflecting boundary condition implies certain things about that there's sort of, in principle, three types of perturbations in the early universe. And it implies several conditions on those primordial perturbations that then naturally see. So I would say it explains them. In other words, it's a single rule that explains several different
Primordial
effects.
vorticity?
It eliminates primordial vorticity, and we do not observe primordial vorticity. So it sets it to zero, and as far as we can tell observationally, it is zero.
Okay.
Yeah.
So why are we saying there's no early gravitational wave observations? As far as I know, we haven't observed the gravitational wave background yet at all. So,
exactly. So what we've observed so far is that it is compatible with zero. So we have not detected any non-zero amplitude for primordial gravitational waves. By the way, these conditions don't set the primordial gravitational waves to zero. There's another argument that I will come to later why this model does, we think, predict that the long wavelength primordial gravitational wave spectrum is zero. So like you say, that the observations will never be able to show that it's strictly zero. They just have been giving tighter and tighter upper bounds on it. So by now we know that whereas the simplest models of inflation predicted that there should be a comparable amount of primordial tensor, that the amplitude of the typical amplitude, the so-called amplitude of the power spectrum of the primordial density and gravitational waves should be equal. Those models have now been ruled out. There's other models of inflation that are perfectly still compatible with the data, but anyway, but inflation is ambiguous on this point. But in any case, we predict that it should be zero, although not by this argument, actually, just to be clear.
So does that mean that?
So if they detect it to be non-zero ever, that'll rule out our model. Yeah.
So does that mean that you wouldn't allow a primordial black hole with a non-zero angular momentum?
That's a good point also, yes. These initial conditions rule out black holes in the initial data. Now you could still have, so it's a very interesting question actually, by the way, because there's claimed evidence for quite large black holes already present 500 million years after the Big Bang. There's a question of how those things could have formed and grown that big by that time. And so it's a very interesting question whether those are really black holes by themselves and how they formed. But yeah, but there are ways to, when you say primordial black holes, it's important to just not confuse two things. One is black holes in the initial data that would spoil this condition that the initial data was an FRW universe with these small perturbations satisfying these reflecting conditions. Those are ruled out by this. So if there's any evidence for that, we would be ruled out. But they can still form by other mechanisms quite early, just not at the bangs.
By non-stellar collapse with some gases or something.
Exactly. Yeah. By some other mechanism than just a normal star forming and exploding. Okay. So now I want to discuss another reason that we think is this picture is interesting, which is the explanation that it gives for the primordial, for the dark matter. Okay, so here I have a table of the particles in the standard model of particle physics. And in the minimal standard model, as it was originally proposed in the 60s and 70s, as the table shows here, every fermion comes in both a left-handed and right-handed partner, except the neutrinos, which are purely left-handed and they don't have a right-handed counterpart. So they're sort of oddballs in the original version of the standard model. Now, but then in the late 1990s, we observed neutrino masses and oscillations. And the simplest renormalizable explanation for that is that actually there are right-handed neutrinos. So the neutrinos have a right-handed partner just like everybody else. That then turns out to neatly explain the neutrino masses and oscillations. And the reason we don't see the right-handed neutrinos, we haven't directly detected them yet, is that by the pattern of the representation, how everybody transforms under the standard model gauge group, the right-handed neutrinos are uncharged. They're inert under all of the standard model gauge transformations. So they just don't couple to any of the three forces, and that's why it's much harder to see them. But okay, so if you go back to the original standard model without right-handed neutrinos, that model just does not have a dark matter candidate in it. Okay, there's no particles in that theory that are both stable, and we have not yet detected them directly by some non-gravitational mechanism. So if you now go on to the standard model with right-handed neutrinos, which is as I say, the simplest one that's compatible with neutrino masses and oscillations, simplest renormalizable one, let's say, that's compatible with neutrino masses and oscillations, then now there's exactly one particle in this table that can still be the dark matter. Namely that if you look at the three right-handed neutrinos, actually it turns out the neutrino oscillation data imply that two of those three have to be unstable and would have decayed in the very early universe. But one of them is perfectly compatible that it's with the data that it is stable. There's a simple symmetry that would stabilize it. And that's the only. So in this model, which is what many people now call the standard model, that's the last remaining dark matter candidate in the theory. And so we would like that would be the most minimal, elegant explanation of what the dark matter is. You don't have to invent some new physics beyond the standard model. It's just one of these three right-handed neutrinos. But the problem is, okay, so the good news for that particle being the dark matter is that the same symmetry that makes it stable, that prevents it from decaying, because you don't want it to observationally to match observations of the dark matter, it has to stick around for the age of the universe. There's this symmetry that stabilizes it, but the same symmetry that stabilizes it cuts it off from the rest of the standard model. So not only does it not talk to the gauge forces in the standard model, but it kills the interaction between the dark matter and Higgs field. So it really just does not talk to any of the other particles in the standard model, except via gravity. So that's good. That sounds just like what you want for dark matter. It's stable and only talks to the rest of the world via gravitational interaction. The only drawback is that then you have to figure out how you actually produced it in the first place. I mean, we see the universe is full of this stuff today. So how did it get there? How did that abundance get created if it only talks to gravity? So this CPT symmetric picture gives a nice explanation for that. It's very analogous to the explanation to Hawking's explanation. It's actually more than analogous. It's closely parallel to, it is just Hawking's, it's the same as Hawking's explanation for why particles are radiated from a black hole, but applied to this symmetric cosmological spacetime. So in the black hole case, the idea is, when you're in a curved spacetime, in Minkowski space, there's a quantum field theory in a Minkowski spacetime typically has a unique vacuum, like the standard model is believed to have a unique vacuum that's compatible with the full symmetry group of the Minkowski background. And also all inertial observers agree about what the zero particle state is. But in a curved space-time, that's generally not true. Generally, different observers in different parts of the space-time and in different states of motion will disagree about which state in the Hilbert space is the zero particle state, is the vacuum. And that's, in particular, that's true in a general FRW spacetime. But in this double cone spacetime, with this extra symmetry, time reversal symmetry, it turns out there is a preferred state, the CPT symmetric state for particles living on that background. And so now if you say, okay, you imagine that the particles are really in that preferred CPT symmetric vacuum state, but we, a late time observer in the room here, we define a different vacuum state. And so if using our definition of the vacuum state, our number operators, we calculate what is the abundance of these neutrinos that are really in the CPT symmetric vacuum state, we will say that there is they have a non-zero abundance in the universe today. So you can calculate that abundance. We do that we did that in this PRL from 2018. And what you find is that it depends on the mass of the dark matter. And if you want the dark matter to agree with the observed density of dark matter today, it agrees if the mass of this dark matter neutrino is this value, about 5 times 10 to the 8 GeV, or 5 times 10 to the 8 times the mass of the proton. And so in other words, the CPT symmetric state gives a very elegant explanation for how this last remaining standard model dark matter particle could be produced, even if it only talks to gravity. It's produced by the mechanism I mentioned. And if this is true, this makes a number of predictions that can be observationally tested and are being observationally tested. And if any of them turn out to be wrong, again, the theory is ruled out. So the first one is that the dark matter is very cold. That means its velocity should be very non-relativistic ever since early times. There's a lot of different ways that cosmologists try to test this, and so far, all data is compatible with the dark matter being cold. It should have another property here that cosmologists call adiabatic. Maybe I won't get into exactly what that means unless anyone's interested, but that's another thing that people test with observations of the cosmic microwave background. So far are compatible with adiabaticity. One that is being tested right now that's very interesting is that, tested for the first time, is that it turns out that the structure of the standard model is such that, okay, there's 3 heavy neutrinos and 3 light neutrino states. And what we're saying is that one of these 3 heavy neutrino states, two of them decay in the early universe, but one of them is stable and is the dark matter. But it turns out that in the standard model Lagrangian, the same thing that you have to do to make this guy stable also sets the mass of the lightest neutrino to 0. And so observationally, so far, we've measured the mass differences between the light neutrinos, but we have not measured, until recently, we've not measured the difference between the overall offset between those light neutrino masses and 0. So we're predicting that because if this right-handed neutrino is stable as it needs to be the dark matter, that the lightest guy is massless, and so you can then predict what the sum of these 3 light neutrinos should be. It should be some particular value, 60 milli-electron volts. And observations have, that's a number that cosmologists can measure, it turns out, from measurements of large-scale structure, and the observational bounds have begun pressing down on that, and are still compatible with that, actually. So again, we predict that the value should be this 60 MeV, which is really the lowest possible value, because it's the one where you take the lightest neutrino and push it all the way down to 0. Now, a funny thing is currently the case, which is that actually over the past year or so, observational bounds have pushed down, and then they've somehow continued to push down, so that actually now the observations favor a neutrino mass that is even smaller than the putative minimum possible value. And in fact, they like even better if the sum of the 3 light neutrino masses is negative, which no one knows what to make of that. But so anyway, there's either some very important bit of new physics but it's a kind of weak, it's not a strong detection yet, but it is something to keep an eye out for, which is that we're predicting that some of the 3 neutrino masses, once the observations stabilize and get better, that there should be a peak that emerges at 60 MeV. Actually, at the moment, the awkward situation is that it seems to favor negative neutrino masses, which maybe means that there's some missing physics in the theory, or maybe just that, I mean, it's not uncommon in these precision cosmology experiments that that these tensions come and go and iron themselves out over the years.
The three conditions that I've seen recently mentioned for neutrinos is that the two of them involve the squares of the masses, so that you can't detect the sign. The last one is usually with as the sum of the masses. So I thought sometimes people thought it was the sum of the modular atoms. But you're saying now you would allow a negative.
So it's a very strange situation, which is that it is what you say, that cosmology is really measuring the sum of the modulus. So it should be a positive number. But then some people decided, okay, they wrote this code that had this free parameter in it, the sum of the three neutrino masses, and they compare how well the prediction of that code agrees with the data sets as they vary that parameter, and then they just let that parameter go negative in their code and find that it fits the data even more.
So I agree with you, that's perfectly possible. In fact, Brian Dolan, who's not here today, was just talking about that to Neil last week.
Yeah, so exactly. So it's kind of formally possible. I think probably one shouldn't take seriously the interpretation that it's saying that if it's true that the cosmological data really favors quote unquote negative values of this parameter over positive values, presumably that's not saying that the neutrinos actually have negative mass, because like you say, the parameter is really defined in terms of the absolute values of their masses and summing them. But it's presumably just telling you that there's some missing physics in the model that's yet to be determined. So that'll be very exciting if that's true. I wouldn't personally bet on that yet, but because the data is just not strong enough, and it's a very radical conclusion. But yeah.
Would you be able to softly break the symmetry to get a slowly decaying dark matter and then a non-zero neutrinos?
So softly, which symmetry are we talking about?
The one that stabilizes the dark matter.
The one that stabilizes the dark matter. Softly breaking that symmetry can lead to a neutrino that, instead of being strictly stable, is just very long-lived and slowly decays. But to my knowledge, it would neither give time, but not by a mechanism. So if you just take that parameter and say that there's some Z2 symmetry that sets the relevant parameter to 0, the decay that governs the decay. If you just say that symmetry is not exact, so that parameter is just a constant, a tiny value instead of strictly 0, that does predict that the dark matter should decay at some rate, and you could try to look for that decay signal. You would see a decay to a Higgs boson and a lepton, both at basically half the energy of half of this 4.8 times 10 to the 8 GeV number. But to that model would not predict either time-varying dark energy or negative neutrino mass. It could be that if you added some extra additional physics to the model that was responsible for the soft break, maybe that would. But the only, in the just standard model with right-handed neutrinos, the only consequence of saying that symmetry is not exact is just to turn on this one parameter by a tiny amount. So yeah. But if you have any idea about what may not, I'd be interested. Okay, let's see. So I'm gonna take out my phone so I don't lose track of time here. Oops, I've already lost track of time. So we started at 2:30.
We don't stick to time.
Okay.
We often have seminars and change.
Oh, okay. Well, I'll try to stick to time anyway, but thank you. So let's see. There's a couple of other predictions. One is that the neutrinoless double beta decay rate, which is something which hasn't been measured yet, but experiments, more and more sensitive experiments to detect it are being built. It makes a specific non-zero prediction for the neutrinoless double beta decay rate. Unfortunately, it's very low. So even the next generation, even the coming generation of these experiments won't be able to detect a predicted value. The next generation after that, but so unfortunately, that's a definite prediction, but a bit far in the future. And then the other thing is that it turns out that the same calculation, this discrepancy between the CPT symmetric vacuum and the late time vacuum that leads to the prediction for the abundance of dark matter as a function of its mass, the same sort of calculation you can do for the amount of primordial gravitational waves that should have been produced, and we predict that that should be 0 in large wavelengths. So again, if those are detected, that also will rule out the theory. Okay, so now the next point which we're excited about, and which is a new explanation for the observed homogeneity, isotropy, and flatness of the early universe. So remember, my first 3 points about how the early universe was simple was that the background metric was invariant under 3D spatial translations, 3D spatial rotations, and also had its 3 dimensions, 3D Ricci curvature, Riemann curvature of 0. So, and a hint, we say a hint to the tiny value of the cosmological constant. I'll explain why that's just a hint, but so what's the idea? So the idea, we have it normally, like when I was in grad school, I learned that to explain these first 3 things, flatness, homogeneity, and isotropy, that was why we believed inflation. Inflation was supposed to give a great explanation for those things. So I want to explain to you an alternative explanation that does not involve inflation. And so what's the idea? So step 1, so this is a pair of papers, but from in PhysLab B. I think I put the reference. Oh no. Anyway, they were both in PhysLab B last year. So the first thing is, so here's the Friedmann equation, the sort of relevant, the one of Einstein's equations that's relevant for an expanding cosmological background, and it relates the Hubble rate, the Hubble expansion rate on the left-hand side, to the various contributions to the cosmological matter density on the right-hand side. So there's the first contribution here is the radiation density, which scales with some constant r over the scale factor of the 4th power. And then there's the non-relativistic matter, like you and I, that scales like some other constant mu over the 3rd power of the scale factor. And then there's the vacuum energy lambda, which is constant, doesn't decay with expansion. And then in principle, there can also be, if the universe was not flat but was spatially curved, positively, if the spatial slices were spheres or hyperboloids with a positive or negative curvature, there would be another term here that would go as some constant, positive or negative constant kappa divided by a squared. So we surprisingly, for the first time, we found the exact solution of this equation. So this is the sort of general version of the Friedmann equation with all the stuff we know is there. No extra contribution on the right-hand side from inflation. We're proud of it because Mathematica couldn't find the solution, and I had to spend like a month alone with this great old real analysis textbook by Whittaker and Watson. In any case, the solution is a certain rational function of Jacobi elliptic functions. So there's a polynomial in Jacobi elliptic functions in the numerator and denominator. And that itself is an elliptic function. So what is an elliptic function? An elliptic function is this beautiful class of meromorphic functions. So now here I'm thinking of now the scale factor a of tau, where tau again is the conformal time. And I'm going to think of that function now in the complex tau plane. So I'm going to analytically extend it to complex tau. And the fact that something is an elliptic, so a of tau is an elliptic function. And an elliptic function means that it's doubly periodic in the complex tau plane. So in this case, it turns out to be periodic both in the real-time direction and in the imaginary time direction. And so here I'm plotting the real part of it over here and the imaginary part over here. But the point is, because of this double periodicity, if I give you a function in this fundamental domain, the square here, and I can just get the rest of the function in the whole plane by just repeating copies of that tile to tile the complex plane. Or in other words, really what it's saying is that the function doesn't really properly live over the complex plane. It lives over this square, this fundamental domain, where if I just identify the left and right-hand side and I identify the top and bottom, the square becomes this torus. And so the function really lives over this torus. And so this this is interesting because there's a famous argument that was given by Gibbons and Hawking in the 1970s that was used by them to calculate the temperature and entropy of all the black hole solutions and the so-called de Sitter space solution with a positive empty space with positive vacuum energy. And basically, this is exactly what they noticed about those solutions was that if you analytically extended them to complex time, and then you looked in the imaginary time direction, that the solutions were periodic in the imaginary time direction. And that they had this argument that you could extract the entropy of such a solution in the semi-classical approximation by just calculating the action of the solution around one period in the imaginary time direction. So now we're now just noticing this same thing about our new solution of the general Friedmann equation for a realistic universe of this type. It's always periodic in the imaginary time direction. So we can also do this thing where we calculate the action around one period and get a formula for the gravitational entropy of a general universe as a function of its cosmological parameters, these constants r, mu, lambda, and k. Now you can ask, okay, for what values of the cosmological parameters is this entropy highest? And so the first interesting point is that it's highest when it's highest for universes for which this contribution, the kappa contribution, the contribution that would be present if the universe was not flat, it's highest for universes where the non-flatness is always unobservable. So it's universes that transition from, at early times they're dominated by radiation, at late times they're dominated by vacuum energy, but then in principle there could be a period in between where curvature comes to dominate, but the entropy is highest for universes where the curvature is always utterly negligible. The universe passes from radiation domination to vacuum energy domination without an observer in that universe ever seeing any sign of the large-scale curvature of the universe, just like our own universe. And then, if you also, now so far I've been talking about purely homogeneous and isotropic Friedmann, Robertson, Walker universes, but we can also do the calculation where we add little perturbations like are observed in the early universe. And if you redo it in that case, you find that okay, so I was saying here, sorry, for the FRW case, you find that the entropy is biggest for universes that are spatially flat, and also it's bigger and bigger the smaller lambda gets. So tiny positive values of lambda are favored; they make the entropy huge. And then also now, when you add tiny cosmological perturbations in the early universe, small inhomogeneities and anisotropies, you can do the calculation there too, and you find that, well, if you just let arbitrary perturbations be present, some of them cost entropy, some of them add entropy. And so, in general, perturbations are neither favored nor disfavored. But if you say the Big Bang is a mirror and you restrict to cosmological perturbations that satisfy reflecting boundary conditions at the Big Bang, then all those perturbations turn out to cost entropy. So the highest entropy state is the one where the universe is spatially flat and the primordial perturbations, the primordial inhomogeneities and anisotropies are as small as possible. A universe that's homogeneous and isotropic, in other words, is favored, and with a giant cosmological constant, with a tiny cosmological constant. So yeah, so I could just summarize it here. So the gravitational entropy we find is largest for universes like ours, which are homogeneous, isotropic, and flat with a tiny positive value of the cosmological constant. So it's I think very striking that this is the case, and that it just follows from taking seriously, the known standard model of particle physics coupled to general relativity, and does not involve adding new physics or adding a new cosmological epoch associated with inflation. So the picture, I say, a measure on the space of universes. So the picture we have is that a proposed interpretation of this gravitational entropy is that, you know, as you reach into the bag of possible, that it's counting gravitational entropy associated with a given space-time is counting the number of gravitational microstates associated with that macroscopic space-time, and that as you reach into a universe and select a microstate, it's telling you which macroscopic FRW universes or FRW-like universes are most likely to emerge, and you know, it's striking that the answer is one like our own. Okay, so let's see. So I wanted to make I think just two other points here. So one is about the arrow of time. So, you know, an observed fact about our universe is that the entropy seems to have been very low, you know, got lower and lower as you look back toward the Big Bang. And then it seems to be getting further and further as we get far from the Big Bang. And that's the so-called thermodynamic arrow of time. And there's a question, why is that the case? I mean, why was the entropy, you know, lower close to the Big Bang and higher when the universe is larger? Why couldn't it have been the other way around? So here, this picture gives a interesting new perspective on that, which is that, okay, so if you take seriously these analytically extended solutions, and you consider fields living on this extended background, and ask that they respect the reflection symmetry of the background, well, you find that a field living on this space-time, first of all, it is analytic down here, so it extends analytically across the bang. The solutions of the field equations for fields of different spins can all analytically extend across the bang. But if you now follow them up to the future boundary, where the universe, the so-called de Sitter boundary, where the future boundary, where time goes to infinity, and the universe is dominated by vacuum energy, they're non-analytic up there, so they have an essential singularity up at the top boundary. So if you demand both symmetry under reflection across the bang, and you take seriously the analytic properties, the combination ends up implying a reflecting boundary condition down here. But because you can't analytically extend across this boundary, there's no corresponding reflecting boundary condition imposed at the future boundary. And so, you know, that's the idea is that's the explanation of the arrow of time, that this reflecting boundary condition forced you to be in a very special part of phase space down here at the Big Bang, the part corresponding to this reflecting boundary condition. But then as you got further away from the bang, you're under no such constraint at the other end of space-time, at the boundaries far from the bang. And that's why things have wiggled into more arbitrary configurations as we get further from the arbitrary points in phase space as we get further from the bang. Okay, finally, to end with a little bit of a speculation here, the hope is to give so at the moment, I've just been inferring from observations that there seems to be a reflecting boundary condition at the Big Bang. And then I've been trying to say, okay, what if we assume that's true and see what other things it explains? Of course, it would be even better to have some good fundamental explanation for why there's a reflecting boundary condition at the Big Bang. So here's a speculation about that. So there's an old idea due to Hawking again, that for the so-called wave function of the universe, so, you know, Hawking made this argument that, you know, there seems to be sort of two kind of rules that you need to use in cosmology. On the one hand, there's the usual rule that if I give you an initial condition, and if I want to calculate, there's one rule that if I specify some initial state and some final state, and I want to calculate the probability to go from that initial state to the final state, fine. I use quantum mechanics for that. And so, but then in cosmology, it seems like you need an additional rule, which is, you know, what selected the initial state? And he said, you know, wouldn't it be nice if there was only one rule instead of those two, instead of having to make up if the same rule you used for the first question, going from A to B, somehow also answered the second question. And just to take it a little bit further, it's, in a sense, quantum mechanics is giving you some sort of, it's like a square root of a probability theory. It's like, it's giving you the conditional probability for B given A, or in other words, it's giving you the square root of that. But just like there's another question you can ask, which is, what is the probability of B not conditioned on A? What's the unconditional probability of B? And so his proposal was maybe the unconditional probability of B is just so, whereas the conditional probability of B given A was the path integral over all configurations, the amplitude for that quantum mechanical amplitude was the path integral over all four-dimensional configurations that interpolate between A and B. Maybe the unconditional probability for B is the path integral over all four-dimensional configurations that have as their only boundary B and just have no other boundary. Okay. So it's an elegant idea. Unfortunately, it famously ran into theoretical problems, and it also just seemed to, in the simple cases that when evaluated in simple cases, doesn't seem to give the right predictions for our universe. So the question is, but the thought behind it seems really nice. And is there a way to resurrect it? So we have another alternative proposal here, which is that the unconditional probability for a given state B, we propose is the path integral over all configurations that interpolate between B and the CPT conjugate of B. So now all of those interpolating configurations have this kind of topology like shown here, that at least in real time, that in order to get from one state characterized by a given scale factor to the other state characterized by the opposite value of the scale factor, they have to pass through a big bang with scale factor equals 0 in between. But that it's the path integral over all of these configurations that gives the wave function of the universe. And because of the symmetric way in which it's defined, it's plausible that the saddle points of that path integral themselves will be these reflection symmetric configurations like the ones we actually see in cosmology. Although that's something where really that needs more careful love and attention to show properly. But that's a guess about what the answer might be. And anyway, it's one thing we're working on. Now, there's one important thing to say that there's one very crucial observation about the early universe, which at the moment inflation models can explain, and that we gave a proposed explanation for, although I've come to not believe our original proposed explanation, and I'm getting excited about an alternative possible explanation, which I think is more elegant and involves less. We had to make so the observed fact, which if you're a cosmologist you would have noted that I haven't talked about so far, is the 2-point function, the primordial perturbation spectrum of the primordial scalar perturbations. That's the thing that we measure to be a power law with a certain amplitude and a certain nearly scale invariant spectral index. So that's a very important thing we want to explain. It's kind of the last in my original list of topics that I haven't had a chance to talk about. So we did have a paper last year giving a proposed explanation for this, but it involved adding new fields beyond the standard model, which I would love to be able to explain it without adding anything beyond the standard model. And until recently, I thought we couldn't do that. Now I've gotten excited about a possible way to do that. I'm happy to talk to people about that afterwards if they're interested. But anyway, just so I would just say, stay tuned about that. And in the meantime, because I'm now more excited about that, I won't really bother you with the details of the previous solution, which does have very interesting things about it. But personally, if I was going to, according to my gut at the moment, if I was going to bet money, I would not bet on it. I would bet on this new thing. But so anyway, I won't bother you with that for that reason. But anyway, I guess that's it. That's all I wanted to say. So thank you. Oops, sorry, wrong end slide I put in. This is not happy birthday to you. But anyway, so thank you very much for listening. And I gave two. Yeah, unfortunately, this whole story is spread out over a number of papers now. But if you were if you wanted to, if you were interested, here's two short ones that you might get most of that sort of thing. Anyway, thanks very much. Yes, yes.
About CPT. So I'm familiar with CPT as a symmetry of endpoint functions and Minkowski. But I'm not.
What is it?
familiar
What is
with
it?
CPT invariance properties of a curve space-time.
Yes, yes. So when you have so really the question is so in an FRW space-time in general, you ordinarily have the normal symmetries of the isometries of an ordinary FRW universe would be three-dimensional spatial translations, three-dimensional spatial rotations, and spatial parity. But like you say, in an ordinary FRW universe, there just would not be time reversal, would not be an isometry of that space. Now, in these special class of spacetimes we're considering, there is one point at which you can do a time reversal isometry. And so it's a bit different than in Minkowski space, where in Minkowski space you have one point, let's say t = 0, where you can do a time reversal isometry, but then you also have time translation symmetry, which you don't have in FRW. So you can take that point of reversal and translate it to anywhere else. So you can really reflect about any point in Minkowski space. So that's the first thing. In FRW, there's only this one special time about which you can reflect, but then you can ask which vacuum then respects all of those symmetries and is invariant under all of the symmetries, and it ends up giving a condition like if if you think about normally in QFT you might take your field that you're quantizing, and in the canonical quantization approach you would write it as some sum over modes of. You would find a basis of solutions for the field equations, and you would split that basis into positive frequency solutions and negative frequency solutions. And in front of the positive frequency solutions, you would put an annihilation operator for the corresponding particle. And in front of the negative frequency solutions, you would put a corresponding creation operator for the corresponding antiparticle. And again, in Minkowski space, that split, there's all inertial observers agree about how to take a basis of solutions and split it into the positive frequency and negative frequency ones. And now the question is, in a more general curve space-time, how to do that. And different observers will disagree about how to do that splitting. But it turns out that if you want to define a state in FRW that's invariant under this extra t goes to minus t, it ends up determining that these guys have to satisfy an extra condition that basically says that the positive frequency solutions are equal to the negative frequency solutions at the when reflected through the bang. And so that there's this extra. Anyway, there's this extra condition you can use to pick out the right the solutions that define a vacuum. Yeah.
The other thing, you then have a kind of firm prediction, although that studies it to verify experimentally that you have a dark matter candidate which is 10 to the 8
Yeah. Unfortunately, it is hard to directly.
That's pretty.
If it's really stable, it's unfortunately, as far as I can tell, it's impossible to detect.
And
it could. It's like I forget who brought it up, but someone brought. Oh yeah, you mentioned that symmetry could be softly broken. So it's perfectly compatible with everything we know that it could be not perfectly stable, but just long-lived. In which case, you do get a very precise prediction for what the decay products should look like. You should see a line at some very particular energy, 2.4 times 10 to the 8 GeV. Unfortunately, you just don't know how high that line is. So it could just be.
And it's slightly related to your neutrino question, which maybe would make the unconnected to what you're doing. If you've got a supernova these days, you can detect these neutrino fluxes some days or weeks before radiation, which means the neutrinos can't decay until they at least get to us. We don't have anything to say about those.
No, everything for us is, so those neutrinos that are propagating to us are the light neutrinos. So those are, apart from the fact that we predict that the lightest guy is massless, we agree with just the standard model about everything. So it should just look like, I mean, it is the standard model. So that issue of detecting distant astrophysical neutrinos turns out to not be the most sensitive probe of the mass. So in other words, the distinction, the one kind of novel thing we contribute that the mass is strictly zero. The difference between that and the tiny masses are not detectable in that sort of experiment. By the way, yeah, I realized I forgot to mention one other recent observable thing, which is a bit related to this that we haven't written up yet, but it's a kind of obvious thing. I hadn't thought about it recently, but so in ordinary Big Bang cosmology, what happens is that things cool down. You start off at very high temperatures with all the 100 degrees of freedom in the standard model in equilibrium with the thermal bath. But as the temperature drops below their mass, those particles annihilate, and you end up at low temperatures. Once you get down to an MeV or something, a temperature of an MeV, you just have electrons and positrons and neutrinos and photons left over. And protons. Those are the only things in the thermal bath, the only relativistic degrees of freedom. And then the neutrinos at some point decouple, and then the electrons and positrons annihilate, so that right after the neutrinos go out of equilibrium with the thermal bath, the number of degrees of freedom drops. And so there's a prediction that today in the universe, in addition to the cosmic microwave background photons, there's also a background of neutrinos, which is at a slightly different temperature, a predictably different temperature than the photons, but contributes to the radiation density and contributes to how fast the universe is expanding, and in principle can be detected. So analogous to that, since we really want the radiation era to go all the way back to the Big Bang, there's a corresponding process which happens at the Planck temperature, which is that the graviton background decouples very analogously to how the neutrinos did. And that also makes a non-net, so that you can also then predict it. Again, it has a slightly different temperature today than either of those other two backgrounds, but it's some nearby temperature, and so it should shift the number. It should act as if there was a little bit more neutrino relic density than there really is. So it should shift the predicted effective number of neutrinos, which are measured by observations, a little bit higher than the value that you would have if you really just had neutrinos and no gravitons. And so that's another thing which I only recently realized was actually it's not yet a detectable shift, but it will be a detectable shift. It will be. So there's a new experiment. The next generation cosmology experiment is called the Simons Observatory. That's another big experiment of the cosmic microwave background measurement. It's coming along, being built right now. It's about to start taking data. That, according to its projected error bars, it should be able to detect this shift weekly, like between 1 and 2 sigma levels, and not very strong evidence for it. And then, so you need to go to a next generation after that to really detect good evidence for it. But the point is, it's not like it's another realistic thing you can check. It's a very precise prediction for a particular shift in this observable number. And unfortunately, like all these things, it's a little bit in the future, but it's not too far in the future. Yeah.
So, that's what you're thinking about in terms of particles on the surface of the Are you imagining that?
So particles on the surface of
the surface of the Big Bang surface of the atomic star. Are you imagining if they stay like entangled, whatever pair forms, they stay entangled with whatever occurs in positive towers occurring the same in minus tau, or do you imagine that as they evolve, the universe look different?
Good question. So, needless to say, we don't have observational evidence to guide us on that point. Yeah, it's basically another way to say it is if you take this picture where I was mentioning this picture where you take a 3 configuration and CPT conjugate, and you path integrate over all 4 configurations that interpolate between them. There's a question whether when you say an allowed configuration there, do you assume that every configuration Do you allow in the path integral is itself symmetric, or do you allow arbitrary asymmetric configurations between them? And we've gone back and forth about this. I don't really know what the right answer is. That's the bottom line. I have kind of arguments that I can tell you later. I have arguments that seem to go both ways. So I have different arguments that seem to argue for different conclusions, and I don't know. Good, interesting question. Yes.
So we live in an isodominated universe. Could the sort of negative tau universe be anti-isodominated?
That's another good question. Yeah, that's a good point. So a point which I didn't mention here is that really kind of microphysically, this quantity probably, if you look at a microphysical model like one based on an oscillating scalar field that might behave effectively like a fluid with a non-relativistic mass. Those models all give an absolute value for mu here. So it's sort of strictly positive by definition. So I think of this as just being probably just being a formula that's kind of this term in this formula, I think, should be regarded as a approximation that's good far from the bang when the particles are non-relativistic. As you get close to the bang, non-relativistic particles, they all become relativistic. So they're not really described by this formula once you get very close enough to the bang. So I don't think, it's an interesting question. It's another question that I think the answer is, I think the answer is that it's positive on both sides. But that this term shouldn't be taken as an exact expression.
So you started with the scale factor A tau equals tau, which is exactly the radiation fraction spectrum. So that switches off the mu and lambda and kappa.
Yeah, that's just the approximation close to the bang, exactly.
So this is the or A of tau is tau is the approximation close to the bang.
A of tau is the approximation very close to the bang when the universe is dominated by this term. Yeah.
So what basically everything you've been saying is, if I think of the mathematical results you talk about, fields of different scale being able to randomly continue. That's those kind of statements are robust with respect to A of tau is tau plus small corrections. Is that the case?
Yes, good question also. Okay, so first let's consider the case where we turn off this term, because this sort of term, which is not this one guy, which is really a non-exact term, is, let me come back and mention that. So, because it's a bit of a more subtle story. So if you forget about the non-relativistic mass term, but you include the other three terms, radiation, lambda, and curvature, then the exact solutions are the exact elliptic function solutions have still all these same properties that, even for the presence of mu, they're all elliptic. But when you turn off mu, they're exactly time symmetric about the bang. When you turn on mu, they still have a symmetry that reflects across the Big Bang, but it's no longer along the real-time axis exactly. So it gets shifted off of the symmetry gets shifted off the real-time axis. So it's a bit of a more subtle story about what's going on there. So really, if you formally extend this term to negative A on the other side of the bang, then this term does become negative, which, as I was saying before, I don't think is physical. So when we're dealing with these solutions where mu is turned on, we're always, it turns out that when you calculate this entropy, it's invariant under what real time you evaluate. You're calculating an integral in the imaginary time around the imaginary time period, but you can shift it in the real time direction and deform the contour actually. And by Cauchy's theorem, you get the same answer wherever you go. So, but if you go to our side of the Big Bang and well to our side of the Big Bang, where you think this guy is a good approximation, and evaluate it there. That's the answer. That's the answer we're using. So we don't. I mean, I tend to think that the answer extrapolated to negative values of A, that in that case, is not really physical. That this term is contributing in a non-physical contribution. So yeah. So it's a subtle story. It's unfortunately, you can find more if you give more correct microphysical models for what the non-relativistic matter is, they can have perfectly symmetric solutions about the Big Bang, which presumably, if the Big Bang is really symmetric, are the right ones. But the problem is that then you can't solve the Friedmann equations exactly, so you can't analyze those cases with that physically correct thing. So instead, we can only solve it in this approximation when we use this term, which then doesn't respect the symmetry that we think is really there. That's
so the geometry at tau is your singular indeed, and you'd expect, if you're solving wave equations for bits of spin, you don't get blow up of their energies and things like this. That just disrupts them entirely by adding all sorts of nastiness.
so the solutions are so the kind of notable thing. One way to say it is that the notable thing about the Big Bang singularity, which makes it differ from a black hole singularity or a general singularity formed by gravitational collapse, is that if you consider Big Bang with perturbations but subject to this reflecting boundary condition, then the metric, even at the Big Bang, is conformal to a perfectly non-singular metric. So if you strip off so the singularity is entirely coming from the conformal factor passing through zero. If you remove that conformal factor, the rest of the metric, in the unperturbed case, it's just Minkowski. But even now, in the presence of perturbations satisfying this reflecting condition, it's just Minkowski plus small, perfectly regular perturbations. So that's not to say that so it is true, photon blue shifts as you get closer and closer to the Big Bang. So it does, so a photon has diverging energy if you strictly follow it back to the Big Bang, or maybe it goes up to the Planck scale, and then typical photons get longer than the horizon and freeze. But if you imagined a photon that you could create particles that would particles are hitting each other with higher and higher energy. The center of mass frames of collisions is indeed going to infinity at the Big Bang. But everything is going like, so for example, so any curvature invariants like that are Weil invariant, that are invariant under conformal transformations, remain finite at the Big Bang. But there are some curvature invariants like the Kretschmann scalar that diverge at the Big Bang. But even in that case, they're all diverging as just poles. They go as like 1 over tau, or they go like 1 over tau. And so again, they're perfectly analytic, and there's a pole, and you have to go around it in the complex plane. But so I tend to think of it a bit like that. That if you want to ask questions about what the physics is like right at the Big Bang, you probably need a theory of quantum gravity, and I'm probably not your guy to answer those questions. So if you want to do experiments that had a time resolution of order the Planck time or the Planck length near the Big Bang and ask about that, I think the semi-classical techniques that we're using don't really apply. Actually, that's a whole other situation, which is related to our new. Maybe I actually don't want to back off that much, because we have gotten interested in the idea that maybe you can really just take quadratic gravity and really take it seriously quantum mechanically all the way back to the Big Bang. But at least this sort of, for example, for this entropy calculation, I've just been doing semi-classical gravity just with the Einstein term, none of the quadratic and curvature perturbations you would need to make it a renormalizable theory. And so that I really don't think you can't take that seriously at times smaller than the Planck time or something like that. But for most of these cosmological questions, it turns out they don't depend, they're insensitive to the physics at those very early times. So for example, this dark matter calculation that we did, where I'm looking at the solutions of the wave equations for different particles of different spin. By the way, I forgot to mention, related to your earlier question, they actually all remain perfectly analytic. They're all perfectly analytic functions. And so just like the metric can be analytically extended, all those solutions have unambiguous extensions to the full double cone. But then if you actually ask, where is the dark matter, where is the physics, at what time is there's this so-called Boyle transformation that measures the difference between the CPT symmetric vacuum state and the late time vacuum. Where is that Boyle transformation accumulated? It's not accumulated at the bang, it's accumulated at the moments before and after the bang, or after the bang, where the time after the bang was equal to the Compton wavelength of the particles. In other words, that's way after the bang compared to the Planck time. The temperature was down at near the temperature of the particle's mass, basically. Or the Hubble rate was comparable to the particle's mass. So all the physics that I've talked about does not really require knowing physics, understanding physics at the Big Bang itself. It's a bit like when you go across, when you do tunneling across a barrier. One way is to tunnel straight through and use the Airy functions. There's this up, but you can also use WKB and go just analytically extend the WKB solution around the barrier, and as long as you don't get too close to the barrier, WKB stays good, and you can get to the other side, and everything's okay. It's a bit like that. I think of it as a bit like that. As you have this pole at the Big Bang, and if you really try to just plow through the pole, the approximations you're using of semi-classical gravity are going to break down. But as long as you analytically continue around the bang, if it's a question that you can answer by using analytic continuation around the bang, and just demanding that the asymptotic solutions far away that you get in that way are related by such and such a symmetry, then those things I think are insensitive to the details of quantum gravity at the bang. But this thing we're working on about explaining the primordial perturbations, that actually is different. That really relies on us taking seriously. There's this guy named John Donahue. I don't know if you're familiar with this guy, but he's a great standard model particle theorist, and but also he's kind of the world expert on quantum gravity as an effective field theory, and that's traditionally his thing he's well known for. And he's been arguing over the past 10 years that this theory where you take Einstein gravity and then add the quadratic curvature terms, Boyle squared and the Ricci scalar squared to it. It's been known since the 70s, since Stelle, that that's a renormalizable theory, but usually people don't take it seriously because it's a four derivative theory, so it has ghosts in it. And but he's been arguing basically that you should take it seriously, that the ghost terms actually still give rise to a healthy theory. The consequence of them being present is that if you did experiments up at the Planck scale with Planckian resolution in time or space, you would see those ghosts, their effects would look like they're propagating retrocausally, but that at the long wavelength blurry vision that we have, that the theory still reduces to Einstein gravity with causality in the forward time direction. And anyway, so yeah, if you do take those theories seriously, we think they give a new explanation for where the primordial perturbations come from. But that really does rely on taking theory seriously, really at the Big Bang. But I think these other things I was talking about here do not.
No other questions. Let's thank Latham.
For all the good questions.
That was a great talk.
Thank you. Thanks a lot for coming.
I learned a lot. I probably interrupted you too much.
Oh, no.